let's talk about sex-linked traits. So, the X and Y chromosomes do more than just determine male and femaleness. There's a bunch of traits that are carried in genes located on those chromosomes. And so any one of those traits that gets coded for on those chromosomes is called a sex-linked trait. So that's our first blank here. Traits controlled by genes on the sex chromosomes. If I need to remind you what the sex chromosomes are, those are the X and Y chromosomes. Any traits there are called sex-linked. They are connected to the biological expression of sex. Genetic males, if you recall, genetic males are what code? Genetic males, if you are XY, let's just put that underneath the word male. They are affected by recessive X-linked traits more often than genetic females. Genetic females, just to review, are what code? XX. So just by taking a look at the XX and XY-ness of it all, why would you suggest that genetic males are affected by recessive X-linked traits more than women or genetic females? Sorry? Why is the Y a problem? It's okay, so why is that a problem? You're right, just keep going. That's not why it's a problem. Well, let's go let's go the other way. Why would a genetic female be less affected by a recessive X-linked trait? What do you mean? So if it's both X's and there's a recessive X-linked trait on one of these X's, why might that not actually be an issue? Because there's another X, and it's more likely that this X might have the dominant expression of that trait. And so for genetic females, if they have one X recessive trait, but the dominant version of that trait on the other X, it's not going to be an issue. Males don't have that luxury. It's one and done. If you get the X-linked recessive trait, that's what is going to be expressed in a genetic male. So why? Because males only have one X chromosome. And if there is a trait on there, whether it's dominant or recessive, that trait is going to show up for better or for worse in genetic males. So conversely, females are less likely to express a recessive X trait because two copies of X is present. So there's a chance. Am I going crazy or are you whispering? You were on the phone. Okay, I'm not going crazy. No, you're good. I heard whisper. I wanted to make sure I was actually hearing whispering, or I'm going insane. Because two copies of X is present, so there's a chance a dominant allele covers it up. There is a classic example of this. Hands up if you or anyone in your family is red-green colorblind. Hands up if you or anyone in your family is red-green colorblind? None of you? Cool. When you're ready, flip the page. Mr. Keeley, do you know anybody who's red-green colorblind? Red-green specifically, yeah. Okay. Who is? Whose friend? Which friend? Not in school. Okay, not here. Is red-green colorblind? So yeah, okay, that's exactly what we're talking about here. How many kids?
One child and she doesn't carry it.
And do you know why she doesn't carry it?
She's a girl. She's a girl.
If she were a boy, well, even then, if she were a boy, would she carry it? If she's a boy, then what chromosome has dad given her? A Y. So if dad is the colorblind, interesting. That means your friend is a carrier. Yeah. If she has a boy, the boy could be. It depends on. Yeah. So this is exactly it. I'll draw it on the board because I don't think I have a space for this on. Yeah. No. Yeah. Brooklyn, you're absolutely right. So, just so for those of us who are having a tough time keeping this straight in your head, if her dad is XY and he is colorblind, red-green colorblind shows up on the X chromosome. So it's more than it's an X-linked trait. So your friend, presumably, said she, girl, to become a girl, mom is XX, mom donates one of these X's, dad donates the only X he has, which carries the trait for color blindness. So now your friend is a carrier. Your friend, presumably, assuming your friend wants to have children, is going to get with someone capable of having children. And she's going to donate one of these two X's. Either she donates one of these X, this X, or this X to an offspring. This being the affected X. If she has a girl, it means her partner gave this X. If she has a boy, it means the partner gave the Y. So what that means is there is a chance her son could be red-green colorblind, even though she is not.
So she's not, but she has.
She's a carrier.
Why doesn't she?
Because she has, it's a recessive trait. So we're going to flip the page here. We're talking about how it's a recessive trait. Why? You were about to answer, Brooklyn? Well, the dominant trait is to not be colorblind. Correct. So the X that she got from mom, if the only way for a girl to be colorblind is if mom and dad both donate compromised X chromosomes. Mom would also, like not even just a, well, she could be a carrier. If mom was a carrier and dad was a carrier, and your friend drew the short straw, the crappy X, then she would have been too. So her mom could be a carrier, we don't know. But we do know her mom is definitely not colorblind because there's at least one good copy of that gene in there, the non-color blindness gene. Color blindness is an interesting one because it can take some people a really long time to actually realize that you're colorblind. Because color is something, it's something you experience, right? Like if everyone looks, look at the board behind the Brooklyns. When I was away on Friday, Hobkirk and Coppendale decided to test all my markers. And at least I can look at that board and see that there is a bunch of different shades of green, I think. But I would agree that everything that the Brooklyns have labeled green, I would agree with. There's a bunch of different shades of red up on there. There's a brown, there's a blue, there's a purple. But I can't be guaranteed that what I perceive to be all those different shades is what you perceive to be those different shades. You might agree that the left column is all green and that the middle column is all red. Or you might be like, yeah, those are just different shades of the same gray. If any of you are looking at that board and see different shades of the same gray, you're red-green colorblind. And until you're put in a position where it matters, that difference matters, more than just a shade, you might not know. Are you following kind of what I'm saying? I knew a guy who went through electrical school, and he didn't realize he was colorblind until they started asking him to pull out different kinds of resistors. And if you don't know anything about resistors, there's different color bands on the resistors that give them their value. And he held up two resistors and said, these are the same. And his instructor said, those are definitely not the same. Colorblind. Can't. Let's find something else to do. Coppendale. Yes. Okay. Yeah.
But none of like her family, no one else is in it that is colorblind. I don't know if they have any traces of it, but she's like fully colorblind and everyone else can see color. And she's also a nurse.
There's different kind. I do know there's different kinds of color blindness. Specifically, if you flip the page, I'm going to talk about red-green color blindness. I don't know about other color blindnesses. I do also know that color blindness might not be an eye problem. It might be a brain problem. How your brain processes what the eyes see could be the issue. So I'm specifically referring to red-green color blindness. Clearly there's something else there, because if she's fully colorblind and mom and dad both aren't, well, if dad's not, then it's something else. Either it's a different kind of color blindness, it's a different gene, or there's something more fundamental there. And she knows that she knows, doesn't know. Yeah, interesting. So, this picture is supposed to be an example of red-green color vision deficiency. Now, it's not, because the photocopier is in black and white. So this is what the picture is supposed to look like. If you have colors, by all means, color it in. What red-green color blindness is like is you'd see, okay, there's the inner part of the watermelon, that's red or pink or whatever color you call that. I called it pink yesterday and the C block lost their minds. Whatever, pink, red, does it really matter? As long as you can tell that this is fundamentally different from the outside of the watermelon, that's my point. And then there's this guy here, which is like different shades of green in the entirety of the picture. This is an example of what the difference is between red-green color blindness. And we know that the trait for this particular kind of color blindness is a recessive X-linked trait. So we can take a look at the Punnett square for this. We've got so this is, okay, you said your friend's dad is colorblind? Okay, what's your friend's name? Alex. Okay, we'll say that this is Alex's dad. For lack of knowing for sure, let's just assume he is. Alex's dad is colorblind. If he's not, well, then we've defamed him, and I'm sorry. If he's watching this on YouTube, I'm sorry, Alex's dad. But let's assume that Alex's dad is actually colorblind, and let's assume that her mom is a carrier. Because that's what this means, right? If you have a heterozygous, big B being normal, little b being recessive colorblind. So this person here is heterozygous. So this could be Alex's mom. But Alex's mom here is just a carrier. Doesn't actually have the expression because the dominant normal trait shows up. So this could be Alex right here. Oh, shoot, we screwed this up. Nope, I totally screwed this up. Dang it. Everyone forget everything I said. This is not Alex's dad. Why is this not Alex's dad? Look at the notation. Because this guy's not colorblind. That big B means normal vision. So you know what? Let's make this more interesting. Let's call this Alex. Because if Alex's dad is colorblind, she's definitely heterozygous for this trait. She has the color blindness recessive X, but she's not colorblind. So she also has the dominant normal vision trait that pops up here. Now let's say Alex meets and has children with someone who is not colorblind. This is Alex's normal future partner. There we go. That is better. More personal, because I don't know who Alex's dad is. I also don't know who Alex is, but I know Alex's friend is sitting over there. Alex is heterozygous for colorblindness. Has to be. And let's say Alex's future normal partner is right here. And Alex and this future normal partner start having children of their own. What could those Punnett squares look like? Well, you could have Alex's dominant trait and the only possible X from her normal visioned partner. You could create a totally normal son. But, so this would be a normal vision son. This would be normal vision daughter. But Alex could also have this kind of daughter. This kind of daughter would have normal vision, but a carrier. It doesn't matter which X it is. And this unlucky son, the 1 in 4, is going to be a colorblind son. So Alex has a 1 in 4 chance of passing on colorblindness to any of her children. Statistically, one of those would be a boy who's colorblind. Or, well, no, one of them is going to be, if she had 4, one of them is statistically, one of them would be a colorblind son, one of them would be a carrier girl, one of them would be a non-carrier girl, and one of them would be a son with no issues. Than women? Yes. Because neither of her daughters would be colorblind. Colorblindness, if she married someone that was also colorblind, so she's a carrier, if she found someone who was colorblind, the sons would still be 50-50, but the daughters would be either a carrier or definitely colorblind. There would be no possibility for this one showing up here because dad wouldn't have the dominant B, he'd have the recessive B. So if she met, married, had children with someone who was red-green colorblind, this would not be an option. It would be either XB little b, or it'll be lower b, lower b. The ever elusive rare red-green colorblind woman, which would just be kind of unkind. So go tell your friend that colorblindness in a boyfriend is a definite hard red flag for the sake of her future children, and that she should get the heck out of there. Well, she should figure that out real quick. So that she's not like, I should pause this, I shouldn't out my friend here. Now I'm recording again. Don't do that, gentlemen. Okay. Or women. Okay, so let's fill this in. In this case, the mother, Alex, is a carrier of the trait. Is Alex in grade 10? Yeah. Has this come up in her science class? You should ask her. Tell her you learned all about her issues. Oh, not about her issues. Don't phrase it like that. The mother is a carrier for the trait because she has the recessive allele on one of her chromosomes. The father is not color deficient, so this is presumably Alex's normal future partner because he does not carry the recessive allele. The only offspring with color deficiency could possibly be a male, and this trait is in fact very rare in females for this reason, and more common in males. Yes. No, because carrier by definition means you have the trait, but it's not expressed. Either they have it, or they have it and are colorblind, or they are not colorblind and don't carry it. Because it's X-linked, for a genetic male to have it means it's happening. Nothing X-linked. Nothing Y-linked either. Like for a male, for a sex-linked trait, a male cannot be a carrier. They either will have it or they do not. They cannot be just a carrier, I should say. Because genetic men only have one of each chromosome. There is no way for there to be a dominant and recessive version when you have two different chromosomes. What is there is going to be expressed. You're cool with that? Okay, so that is sex-linked colorblindness. Sex-linked colorblindness, incomplete, and codominance. What I've got for you now, for the remainder of the block and perhaps some more time, depending on how long this takes, is a whole bunch of practice with a bunch of these ideas. So, yeah, here we go. I want you to get started on this and see what happens. How much time, what does this block actually end? Is it quarter after? It's either 30 minutes or 35 minutes. It's quarter after. Half an hour. So here's what I'd like you to do. I will tell you where I will cap the homework near the end of the block, but here's what I want you to start with. I found this Punnett Squared practice packet on the internet, and I thought it was really quite good. So I've given this to you, and I'd like you to try and work through it. There are 3 questions on the front that are similar to stuff we've already done. One is a red and white complete dominance, which is what we started by talking about at the beginning. It's if this trait is completely dominant or not dominant. Completely dominant or completely recessive. Talk about the Punnett squares, talk about the phenotypes, all that jazz. Do the same thing for incomplete dominance and the same thing with codominance. And then tell me what phenotypes would be present. So there's 3 different three different Punnett squares you're going to do, and you're going to look at how the phenotypes show up differently in each case. Then I've got some more here. There's something called a snapdragon, which is another kind of flower. There's a question here about horses, and some of the genes for hair color are incompletely dominant. And then there's a really interesting one. You guys are going to look at blood types. Hands up if any of you know your blood type. Jedediah, what blood type are you? O positive. Okay, so we're not talking about the positive and negative portion of, because so there's multiple ways to type blood. So you're Rh positive. Okay, I'm Rh negative. We're ignoring the Rhness of it all. I just want the letter. So you're O. Nice. You can donate to everyone. You are a universal donor. Love that. But you can only receive blood from other O's, which is bad. Muller, you know your blood type? What blood type are you? You are A. Me too. That means this is true. This would be the genotype for A. So there's a codominance worksheet here that looks at blood type specifically, and it has some really interesting kind of questions that go along with it. Things like Mrs. Brown is type A and Mr. Brown is type O. They have 3 children named Matthew, Mark, and Luke. Mark is O, Matthew's A, Luke is AB. Based on this information, what are the parents' genotypes? And then there's some, if the child got swapped in the hospital, how could you use blood typing to determine if the parents are the parents and whatnot? It's really quite interesting. So we're going to start with those first 3 examples on the Punnett squared practice. If you could get, okay guys, if you could get to the end of page 4 by the end of the block, I think you'd be in a good spot. I have included, should you need it, should you want to use it, if you flip one more page, it says Punnett squared worksheet on the top. It is just 12 blank Punnett squares that you could use instead of drawing all your own. And there's another 12 on the back. If you want Punnett squares, you don't want to draw them yourself, they're there. See what you can do with that. I will walk around and help as needed. Yeah, codominance, incomplete dominance, and regular dominance. Complete, incomplete, or co. There you go. And your marker said go.